Our project is about hydrokinetic turbines for slow velocity rivers. Here is our table of contents, which we'll be going over this presentation. Hydroelectricity is a crucial energy source for low carbon grids. Unfortunately, many broader rivers do not allow for damming due to shipping or environmental issues. Another method of generating hydroelectricity would be kinetic energy of a flowing body of water. Here we're creating a hydrokinetic turbine, or an HKT, offer the possibilities of renewable generation from river flow, could help supplement variability of solar and wind. The problem is that large volumes of water move through rivers like the Ohio, but the fluid velocity is usually very slow. So we're going to be using a hydrokinetic turbine for slower moving waters, and that requires a duct design to increase water velocity over the turbine blades. We're going to be using the Venturi effect, and we're also utilizing the STAR CCM and CFD software to simulate a duct and determining sizing required for desired water speed in the turbine housing. After designing the turbine, we will lay out a basic Arduino RPM sensor for the device. The main benefits of this are the major challenge of renewable energy is variable, this being sunlight and wind. Providing another renewable energy source provides diversification to meet demands. And using hydrokinetic turbines in slower moving rivers can provide access to new renewable sources for inland regions. Here's the cost of everything. It comes out to about $370. That's with the motor, all of our mechanical bearing shafts, screws, seals, O-rings, and then as well as filament and bonding glue and 3D coating. And then here is our project schedule.
So for our concept map, which sort of informed the whole project, we basically divided it up amongst like the stuff that we're good at with co-ops and the classes that we've taken. So obviously some of the biggest ones I would say that we used are electric machines and drives, electromagnetics, and electric power. And a lot of us had, I mean, I had a co-op with Duke Energy for most of my time at UC, so we used electric power stuff from that, and Kearsten and Cameron both did electrical engineering and MEP stuff at different companies as well, which was helpful, especially for some of the computer-aided design that we had to do for designing this prototype. So before we first started, we did initial design calculations using the continuity equation, which actually we refined this with our simulation further, and it turns out that this doesn't exactly hold, but it was still a good place for us to start for increasing the water velocity. And then we used ArcGIS, which is provided through UC, and connected to the USGS streamflow model to figure out kind of the worst case spots that we could look at on the Ohio River. We got around 1 foot per second is what we decided to base it off of, which is like 0.3 meters per second. It should be noted that there are definitely better parts of the river to descend than the one we selected. Where the river gets narrower, it speeds up. So there are some good places by North Bend that might be more feasible. So our design and simulation, we wanted to do COMSOL, but actually it turns out we didn't have the right package. So we decided to do STAR CCM Plus. It was a 3D Reynolds averaged Navier-Stokes equation, which we solved over this duct, and we basically had the outer computational domain to simulate like it being in a river. The first simulation we did confined, and that's not exactly what we're doing. So we changed it, and we got an increase in the velocity, as you can see, from like 0.3 up to 0.5. So it was basically 1.67 magnification of the speed over the blades, which isn't as good as what we initially calculated, but it's still very good. So for the actual design, our prototype, we started based in SolidWorks, which is provided through UC. Again, we kept the 1 meter diameter entrance duct, narrows down to about 0.45 meters in the turbine chamber, which is where that ring is. Again, we designed it based on 1 foot per second. The blades, I increased the chords. We followed a paper by Knight et al. It's 3D Rams optimization paper that told us how to do the chords and the blade twist profiles. So that was optimized for us already, which was great. And actually the shape of the duct we also took from them as well. So that was useful. And then the generator chamber is there's air on the inside, and it's sealed by a mechanical seal, seat, and 2 O-rings. And then we also 3D printed in PLA a 4-to-1 planetary gearbox to increase the speed at the generator output. So another crucial part that we needed to figure out was the starting torque required for our selected DC YATEC motor. And we got just about 0.42 pound-feet, pretty constant throughout the entire load curve. If it's unloaded, it's about 1.65. So we needed this to figure out if we were going to do the gearbox, which we decided to do it anyways, just because of the speed requirement for this motor. And when we actually test it, we'll come up with a solution to pull out the gearbox if we need to decrease the or increase the torque. So this is also just a simple RPM sensor schematic, which we pulled and put together for using a Hall sensor. If you wanted to figure out the rotational speed of the shaft, you would put the Hall sensor near that shaft, and it would we'd come up and figure out when you would want to brake it or apply a brake to keep it from destroying the generator. Here's some of our progress pictures. We're just about done. We're printing the outer part of the duct, and everything else is ready to assemble pretty much. So we're good to go.
Still a work in progress, obviously. Have you seen the progress pictures? And we are going to use CRC's Lazy River to test the functionality of our hydrokinetic turbine. The water speed has been confirmed with an acceptable range of 1 foot per second, as you can see in the video.
We don't have a flow meter, so that's the best we have.
And then obviously the post-testing conclusion is a work in progress. We still have to build it, which should be done in the next couple of days. And then, so for future work, control system / SCADA for measuring RPM, mainly to control shaft braking in the case of excessive water speeds. For actual commercial production, designing a plastic mold would be best for manufacturing. And if we could use recycled material, that would be the best for the sustainability of the product. Other analysis would be needed as of heat dissipation, generator optimization, structural buoyancy work, and temperature response. So if feasible, utilizing hydrokinetic turbines in slower moving rivers could provide the ability to harness larger rivers like the Ohio for electricity without the large dams required for traditional run-of-the-river hydro. These are the references that we used. And if you have any questions, you can contact us at these emails, and we will get back to you as soon as possible. Thank you for listening.